Last time I had plus like a year ago, you try to like build like a trench thing that just harvests the heat every once in a while for just fun. CSA apps. Like, learn how to avoid graduate. Like I was gonna say like seasonal hot who's the one that sounds I think the tablets are more available other.
So where do I sign up?
It's like what? It's like 2-3 lessons there.
It'd be like 10 hours.
Do random number
Test. Okay, I think that's good. Not too loud, not too soft. All right. So I'm hoping that you guys, enjoy the homework assignment. Really? Okay. Yeah. I'll go over the solution today. Particularly, I will explain, how I got to the answer. Okay, because it's the analysis of the patterns. Okay, that's basically what it boils down to, and also how to relate it to the stuff that we have talked about, permutations and combinations. Okay, so we'll go ahead and take a look at it. I prepared a document already. I just have to unhide it, which is right here. And you cannot see it just yet, because I have to turn it on. So let me turn on, unhide it. Show display. So now we can see it on the projector, and you can also see it on your own devices if you already have a device logged into Moodle. Okay. All right. So the notation is not that important, but what we'll do is we're going to focus on how do we come up with the number of what I would call core patterns. Okay. So let's use some examples, and this time I think I am going to use a spreadsheet to look at all the permutations, because it's just a whole lot easier to get everything lined up, and it's just easy to show it that way. All right, so we'll start with a new spreadsheet, and that's a good question. Let me double check. So according to this, yes, I am recording and with voice. Did I record without voice last time?
I think for 310.
For 310, yeah. I think what I did was I thought it's already recording the voice with this class. So when I started the recorder in 310, I did not check whether the level is flickering or not. Okay. All right. So what we'll do is we'll take a look at a case where n equals to 10 again, and we'll take a look at what is a core pattern. Or I will define what is a core pattern, and then we'll start go from there. Double click, and it's not letting me double click. Okay, well I guess that works too. All right. Okay, when n equals to 10. Okay, let's see. 1, 2, 3, 4. I think I'm missing 1, so j has to be a part. To be a part of this too. All right, so we're looking at the case where n equals to 10 and r equals to 10. When r equals to 10, it means the same thing as when r equals to 9, which is basically we're looking for the longest sequence. So what I'll do is I'm going to define what a core sequence is, okay? Because it's something that cannot be replicated by rotation or by mirror images. So in this case, the core sequence is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is the only core sequence that we can have when we're looking for a sequence of length 10 or 9. Does that make any sense? Because all of the other patterns can either be done by rotating this one, or by looking at it backwards, or basically doing a mirror image, or a combination of the two. Okay. So this is the only one. once we figure out the number of chord patterns, it's easy to figure out the total number of permutations because it's just multiplying, in this case, by 10 for the 10 rotational positions, and then times 2 for mirror images. Is that okay? All right. So this is an easy one. And then the next one is going to be when n equals to 10 and r equals to 8, because when r equals to 9 is the same thing as when r equals to 10. This one is not too complicated. We can still track everything by hand because we just fixed the first 8 numbers. And in this case, we don't really have a whole lot of choice because this one cannot be a 10. Cannot be a 9, can only be a 10. Because we only have 2 numbers left. If it cannot be one number, it has to be the other number. But that also locks down the only remaining slot because out of the 2 numbers, one has to go here, so the other one has to go to the end. So that means we only got one choice here. We can put a 10 here, but then the 9 has to go here. The second one is to start with a 2, ending up with a 9. So now we have 10 and 1. But 10 cannot go here, so this place has to be a 1, which means the 10 has to be the last one. So 1 here, and the 10 is the last one. Are there any questions about these 2 sequences? We are talking about row 2 and row 3. Are there any questions about these 2? Okay. And then if we start with 3, then we have 3, 4, 5, 6, 7, 8, 9, and then a 10. This time, we can have just about any number here. However, this number cannot be a 2. So we only have 1 and 2 left. If 2 cannot be here, that means we can only put a 1 here. Then the 2 has nowhere else to go except for here. And that exhausted all the cases where r equals to 8. Is that making any sense? Is all good? Okay. Okay, so I'm going to do the same thing with r equals 7, but as we work on r equal to 7, then we'll start to come up with ideas of, okay, can we generalize this so that when r equals to 6, we can apply the same formula so that we don't have to enumerate all the cases and still be able to figure it out, okay? So as we work on this one, we'll start to apply some reasoning to the counting. Okay, so we'll document this and say this is when these are the cases when n equals to 10 and r equals to 7. And I'll even use some color highlighting here. Okay, so let's see, border color, by style. Okay, where does it let me change the color of cells? Right there. Okay, so nothing too fancy, just highlighting which portion is already fixed. There we go. All right, so now we're down to 7. 1, 2, 3, 4, 5, 6, 7. And now we have 3 places where the other 3 numbers can go. The way I would reason this is I would start with the restrictions. In this case, this is where the restriction is, okay? Because 8 cannot follow 7. Otherwise, we'll be double counting a sequence that we have already explored earlier. So that means out of the 3 numbers, we can only have 2 possibilities here. Okay? So the 2 possibilities out of the 2, okay, let me just replicate this one here because there are several ways to do this. So there are exactly 4 ways to arrange 1 to 7, or starting with 1 to 7 when r equals to 7. Out of the 3 numbers left, 8, 9, and 10, 8 cannot be here. So that means we can still have a 9 following the 7 or a 10 following the 7. Okay? So I'll just fill this in like this, 9 and 10. Now when 9 fills in here, that means whatever is remaining can be any one of the 2 numbers. Since we have used up 9 out of 8, 9, 10, so we have 8 and 10 left. So 8 can be the first one, then 10 has to be the last one. 10 can be the first one, then 8 has to be the last one. So within these 2, it is actually the number of possibility or the number of ways to arrange these 2 positions is 2 factorial. because we have two possible choices, and any permutation of those two numbers will work out just fine. Because they cannot continue the sequence already, because the sequence is broken by the 9 in this case. Is that okay? But we also have two choices for this part because we have 3 numbers left. But out of the 3 numbers left, only 1 has to be ruled out, and that's why we only got 2 choices left here. Okay, so kind of keep that in mind. If we end with a 10, or if 7 is followed by a 10, then we have 8 and 9 left. But out of 8 and 9, they can be any order and not be a problem. Are there any questions about this particular pattern where we have 1 to 7 as the beginning of the sequence, and then we have the 3 leftover positions to fill in? Yeah.
The last line you have 10, 9, 8, which is a sequence itself, a sequence of
3.
R equals 3.
Yeah.
Are we gonna count it? Are we gonna?
Right now
Because
we
it's
are
gonna
only.
affect-
Yeah. Right now we're only counting at the most up to a sequence of 7. So if you have a subsequence of less than 7, it's still okay. Any other questions? Because if you worry about subsequences, then everything can still be a subsequence of 1. So we always have a problem. All right, so the next one is starting with a 2, 3, 4, 5, 6, 7, 8. Now we have 3 numbers left. But this is a different problem, okay? It's a slightly different problem because we have 2 restrictions, okay? So I'll work out the actual numbers first, and then we'll go back and figure out, okay, so what is the general approach? How do we see this? So there's only 3 possible ways to do this. So we have 1, 2, 3. Okay. We know that a 9 cannot follow an 8. Okay, so that will leave us 2 choices. So it seems like it is really the same thing as the case where we start off with 1 to 7, but it's not, because the last number also has a restriction of it cannot be 1. So let's start with the case where we cannot end with a 9, or a 9 cannot follow an 8. So it has to be a 10. If this is a 10, then we might think that there are 2 choices, okay? Because we might think that we can put a 2 here and a 1 here, and then a 1, oops, not a 9 here, and then a 1 and a 9 here. But of these 2, this particular thing actually has a, oops, the other one, sorry. This one actually has a sequence of length 8 and not 7. Because the 1 is wrapping around to the 2, and then we count all the way up to 8. So we have a sequence of 8 and not a sequence of 7 anymore. So that's why this cannot be one of the choices. We really only have 1 choice if we have a 10 here, so which is 10, 1, 9. Now what if we have a 1 here? Then we have 2 choices, because we have a 1, 9, 10. That's one possibility. And then we have a 1, 10, 9 as the other possibility. But we don't have 4. Is that okay? So this is a little bit different, okay? So it's not the same reason, because this time we have 2 constraints and not 1. I'm not going to talk about how do we mathematically take into consideration that we have 2 constraints and certain sequences cannot meet both constraints. Okay, so we'll talk about that later. We'll just go ahead and complete the entire thing first. Then we'll go back and try to generalize the equations or the formula. 3, 4, 5, 6, 7, 8, 9. And this is in the same category as the previous 3, because once again we have 2 constraints. A 10 cannot follow a 9, but 3 cannot be preceded by a 2 either. So we have a double constraint again. So with the double constraint, we still have only 3 possibilities. So I will use 3 rows for starting with a 3, ending with a 9. This cannot be a 10, so that means it can be a 1. If this is a 1, this cannot be a 2, it can be a 10, so the 2 has to go here. if this is a 1, cannot be a 1 anymore, because if this is a 1 again, then the next one this one will be a 2. So that is not possible. So this time we have to end with a 2. With a 2 here, then we have two choices, because we can have a 2, 10, 9, or a 2, 9, 10.
That should be a 1.
Oh, 1, sorry. There we go.
No, the 9 should be a 1.
Sorry?
Your last row, 2, 6, 1, 2, 9s.
Oh, okay.
That should be a 1.
That should be a 10.
It's the same.
Oh, 2, 1, 10. There we go. Sorry. Okay, there we go. Okay, so and then we have 1 left. Okay, started with a 4, ending with a 10. But that really is the same case, quote unquote, the same case as starting with a 1, because only one end has a constraint. So you will have 4 possibilities. So we go back to here, and this time we go 4, 5, 6, 7, 8, 9, 10. And we'll just go ahead and replicate these patterns 4 times. So copy and paste, paste, paste. There we go. So we have 1, 2, 3, as the numbers remaining. We know the last one cannot be a 3, but it can be any other number. So you make use of that constraint first. So the last one can be a 2, can also be a 1. If the last one is a 2, then where we put the 1 or the 3, where we put the 1 or the 3 does not matter here. So we can start with a 1 and a 3, or we can start with a 3 and then a 1. If the last one is a 1, then we have 2 and 3 left. But where we put the 2 and the 3 should not matter. So both of those patterns will work. So is that okay? Now these are the core patterns, and for each core pattern, it will times 10, which is n, to get the 10 rotational duplicates or clones, and then you will also times 2 after that to get the mirror images. Okay. But at this point, I think we have enough to try to calculate using n and r to come up with a formula to basically say, what if r equals to 7, n equals to 10? How many core sequences can we get? So I think we can generalize already at this point. Okay? But the important part is the reasoning. Okay? So the way I did this, it is all written. So if you go back to the notes here, it's all written here. But when you read this stuff without me actually showing you in a spreadsheet, it can get a little bit confusing. So I want to talk about it with a spreadsheet first. Okay, oops. Go back to here. There we go. So we take a look at these 4 sequences, and we say, okay, but how do we come up with the number 4 when we only want to refer to n and r? You probably already see that the number of core patterns is not so much a function of n versus r. It's more like a function of what is n minus r. N minus r is more important than n itself. N is being big simply means that you have more rotational clones. That's basically it. But the difference between n and r is actually what makes this, what creates this pattern. Okay. So one thing we notice now is the difference between n and r is important. So let me use a notepad here, because I need a little bit of space for kind of more free form formula. So I'll just stash it next to here. There we go. All right. So what we want to do, or what I will do, is I'm looking at this position here and say, how many choices do we have? We know that we only have 2 choices. Well, 2 is good, but it's not expressed in the terms of n, r, and stuff like that. Yes?
Minus r minus 1 factorial.
The first 2?
Well, what I was thinking is like 2 can be expressed if r is 7 and n is 10.
Correct. But 2 and 2 factorial are exactly the same. But conceptually, they're different things. Okay? So what I want to say is, we have 2 choices here. That's not because of 2 factorial. It only has to do with n minus r minus 1. Okay? All right, so I'll just explain it here. N minus r minus 1 is the number of choices for the slot right after the sequence. Okay, is that sufficient? Okay. But that only accounts for one position. But it does take up one of the three remaining numbers. The other two numbers that are remaining, they can be in any order, which means 2 factorial would account for that. So let me just write that down here. N minus R minus 1 factorial is the number of permutations after the, let me see, N after the R plus 1 position. How about that? Yep.
So the first one, isn't it N minus R and that's it?
It's not N minus R because in this case N is 10, R is 7.
Oh, we're talking about 7 precisely?
Yes.
Because if we generalize it, it will be for N equals 10, for R equals 10.
But we'll use the case where R equals 7 as a clue to figure it out. Yeah. Because if the case is too specialized, it is harder to actually see how the numbers work out. So when the cases, when it's more general, you can see the pattern a little bit easier. Okay. So together, then we have, in this case, we have the total number. So N minus R minus 1 times N minus R minus 1 factorial it's accounting for the 4 here, okay? If you look at the row numbers, we are accounting for row 5 to row 8. That's what this number is. Is that okay? Well, let's see whether it makes sense or not. N is 10, R is 2. Excuse me, N is 10, R is 8. 7, sorry. R is 7. 10 minus 7 is 3, 3 minus 1 is 2. 2 is 2. 2 factorial is also 2. 2 times 2 is 4. And we have 4 rows. Is that okay? But we have to remember that there's the opposite of this, which is the sequences starting with a 4. So now we have to go back to this expression and say, okay, let's multiply this whole thing by 2 for the 2 sequences that have 1 constraint. Because both of these only have 1 constraint. If you look at these sequences, the constraint is after the 7. But the last element has no constraint because nothing can precede a 1. Is that okay? When you look at the last 4 sequences, starting with a 4, these have exactly the opposite problem because nothing can follow a 10, so there's no constraint after the 10. The constraint is the last element because we have to make sure that 3 is not preceding 4. So that's why they're in the same boat, and the way we count the number of outcomes in both of these sequences will be the same. So that's why we have a times 2 to this formula here. What about the stuff in between? That's actually a little bit harder, okay? So the first question is how many subsequences do we have in between? Okay, we have 2 to 8 as one, we have 3 to 9 as the other one. Okay? So the number of sequences, starting with 2, starting with 3, and so on, turns out to be N minus R minus 1. Is that making any sense?
No. N minus R minus 1 is 2. You have 6.
No, but all of these, the first 3 of the 6 start with 2 to 8. The second 3 start with 3 to 9.
Yes.
So I'm considering, so this number, N minus R minus 1, is only counting
Groupings.
how many sequences of 7 can we have, not counting the first and the last one. Is that okay? Okay, so that's what this number is. Okay, so I'll just write it down here. So there are N minus R minus 1 remaining ways to obtain a sequence of R numbers. Okay? So that's what the n minus R minus 1 is. All of these cases have 2 constraints, not 1. Does that make any sense? Yep.
I thought there were 3 when you had 2 constraints. That's what I'm so confused about. When you have 2 constraints, you have 3, 3, 3. When you have 2 constraints, you have 2, 2, 2. Right?
He's saying that n minus r minus 1 replaces the 2 in the equation right above it. So it says 2 times whatever. We haven't filled in the second half yet.
Right.
We've only said what replaces 2 there.
Okay.
Is that okay?
Yeah.
Okay. Okay, then we can focus on just one of them, okay? Because now that we know that all of these cases have the same issue of having 2 constraints, then the way we count the number of ways to arrange the rest of the numbers that are not a part of the sequence would be identical, or at least we make that assumption. Is that okay? All right? So, in other words, the problem now is once we fix these 7 numbers, basically that's R, how many ways do we have to arrange the remaining positions? That's the question. Is that okay? So we'll start with something that we already know. What we already know is, given only 1 constraint, there are 4 ways of doing things. Okay? Okay. So in this one here, I'll just use the case when n is 10 and r is 7. Okay, just for illustration purposes. Okay. So n equals 10, r equals 7, with only 1 constraint. Okay. Constraint starting with 2. Then we have the following sequences, or following assignments: 2, 3, 4, 5, 6, 7, 8. That's the beginning part. So I will copy and paste this 4 times. Because we're going to use the same rationale as before, because we only want to place the constraint after the 8, but not preceding the 2. So that means we cannot have a 9 here. We can still have a 10 here. So we can have 10 here. We can still have a 1 here. After the 10 is here, we'll say, okay, we have met the constraint of not having a 9 following an 8. So the remaining 2 can be any of the remaining numbers, which is 9 and 1. So we can put a 1 here, a 9 here, and we can put a 9 here and a 1 here. And this one, the same thing. We can have a 9 and then a 10, and then a 10 and a 9. Okay? So these 4 is basically generated based on only 1 constraint. But we want to meet 2 constraints and not just 1. Does that make any sense? So what we want to do is to say, out of these numbers, out of these elements, or out of these sequences, how many of these would not meet the second constraint? That is the question. Yep.
Your mouse pad differs from your Excel spreadsheet.
There's one more.
There is one more. Yeah.
There's one more because I focus on only 1 constraint.
Oh, okay.
Because I want to come up with a general formula so I can compute, okay, so how do we count the number of permutations with the next 3 items that will meet both constraints? We already know how to deal with 1 constraint. That one we know. But how do we deal with 2 constraints? That's the question. Okay. So out of this one, there's only 1 that will not meet both constraints, and that's the one that ends with a 1. Okay. So let's pick out this one here. Okay. This one does not meet both constraints. Okay. I'll just abbreviate it to not both constraints. How's that? Would that be clear enough? Okay, because we are looking at things that can only meet 1 constraint, but of the 4 that can meet 1 constraint, 1 cannot meet 2 constraints. The other 3 can meet both constraints. So the question now is, how do we come up with this number of 1? That's the question. Is that okay or not? Because only in this case it's only 1, but when R is 6, it's not 1 anymore. So let's look at the case when R is not when R is 6. Okay, that will make it more clear. Okay, n equals 10, R equals 6 in this case, and we want to with only one constraint, starting with 2. So we now have 2, 3, 4, 5, 6, 7, and then the rest is just kind of, that's what we're interested in. We know that this cannot be an 8, so it can be a 9, right? So let's just figure this out. Okay, first of all, how many rows should I reserve? I'm only interested in sequences where they meet one constraint but not both. In other words, we're just looking at sequences that do not have an 8 following the 7, but otherwise things can be whatever. So how many are we talking about? We already know that equation, don't we? Of the 4 remaining numbers, 3 can follow the 7. So that's the 3. And then after we pick out that number, whatever is following the 7, we only have 3 numbers left. But the ordering of those 3 numbers is not important anymore. So now we have 3 factorial for those permutations. So we already know that we are looking at 3 times 3 times 3 times 3 factorial. 3 factorial is 6. 3 times 6 is 18. So we already know that we're looking at 18 possibilities here. 1, 2, 3, 4, 5, 6. Okay, I'm getting lazy. Bam, bam, done. It's only when we start to work with more, I would say, hairy cases, then we can start to see the pattern. Okay, because the previous case only has 1 that has to be kicked out that does not meet both constraints. This one is going to have more. Okay, so we'll take a look at, okay, but what is more? The next number cannot be an 8, can be a 9. Okay, so we have 9, 9, 9. Okay, that's 1, 2, 3, 4, 5, 6. Okay, and it can also be a 1. Okay, so let's put a 1 here. 2, 3, 4, 5, 6, and it can also be can be a 10. Yep, there we go. So a 10. Okay. So that takes care of the number that is following the 7, and then the remaining can be whatever. Okay. I don't really want to spend the time to illustrate all the remaining ones, but it is kind of important to do that. So let's do that. Yeah, I don't really have a choice because I want to count the numbers of sequences where it meets only one constraint but not both. Yep.
Can we kind of just reason it out from this point, though?
You can reason it out. Yep. So let's try to reason it out. Okay. We know the last one cannot be what?
1.
Cannot be a 1. So how many choices do we have? So you work your way back. Okay. The last position cannot be a 1. So we can say it's not. It is not a 1.
There's 2 other choices.
So there are 3 other choices, right? But there are 2. Well, there are 2 other choices, not counting this one.
Yeah,
Right?
Right.
Yeah, go ahead.
So if we just look at the subset where 9 is the number that follows the sequence that we're looking at, so just that top section, how many cases are we going to have to exclude? How many of them are going to end in a 1?
Yep, that's basically what we're asking.
Oh, I thought you just came up with an answer for that.
Oh, no, I have not disclosed the answer yet. So that's why we want to take a look at the pattern. Now the permutation is whatever number is left, we have 1, let's see, 7 numbers. We have 1, 8, and 10 as remaining numbers, okay? So out of those, how many times do we end up with a 1? is exactly twice. Okay? With this one, it's not possible because 1 is already used. So none of these can end with a 1. Out of these, once again, we have 2 that can end with a 1. But why is it 2? Say again.
The remainder minus 1.
The remaining minus
So
1.
you have like 3 digits left over, you can replace this 3 places, and you subtract 1 where there's going to be 1 permutation, which is going to be at the end.
Okay. So out of the total 4, we're going to take out 4. Because 2 out of these is going to end with the 1. 2 out of these is also going to end with the 1, and those are the ones that we have to kick out. The rest would actually meet both constraints. So now the question is, okay, now that we know there are 4 of those, why are there exactly 4? What is the formula that tells us there are exactly 4? Yep.
To give it a shot.
Yeah, go ahead.
So, if we just look at the subsection where there is the 9s again, like I was talking about before, then it's really a question of permutation.
It is.
And then if you like talk about placement of the 1, I kind of think of it backwards, like you're placing from the end.
Yep, you start with the end. Yep.
Yeah. The ones that start with 1, you're going to have 2 factorial of those because
Correct.
You can switch the other ones.
Yep. Okay, so you basically are looking at the end here, and this time you're saying, okay, the constraint is I want to put a 1 here already, but I have 4 numbers. I have 3 numbers left because this is when n equals to 6. Okay, so we have 1, 2, 3. Let's see. There are 4 numbers here. Okay, so that's good. But the first one already has a constraint on it, which is it cannot be an 8. Okay, so we know this one cannot be an 8 already. Okay, so now we want to find out, okay, how many ways can we come up with number assignments where the first one cannot be an 8, the last one has to be a 1, the ones in between, we don't care. That's the question. Okay, this is one choice, is taking out 1 out of the 4 numbers that we can choose from. This one is taking out another choice, but it also has a constraint of n minus r minus 2 in this case. That's the number of choices where this number can have out of the possibilities. These 2 don't really matter. So that means between these 2, we have 2 factorial, or I shouldn't say 2 because I want to refer everything as n versus r. Okay? So out of these 2, we have n minus r minus 2 factorial permutations. So when you multiply 1, because there's only 1 choice here, so that's 1. So you multiply 1 to n minus r minus 2, which accounts for the number of values that can go here, and then multiply n minus r minus 2, which accounts for the permutation of whatever goes in between. That's the number that we are looking at. Okay, let's double check, okay? Because we want to double check and see whether this makes sense in the example that we are looking at or not. 1 is 1, no big deal. N is 10, r is 6. 10 minus 6 minus 2 is a 2. 10 minus 6 minus 2 is also a 2, but this is a factorial. Okay, but 2 factorial is just 2. So we have 1 times 2 times 2, which is 4, which matches the number that we already know. Yep?
So the second 2 is a factorial, those are the polar numbers in the center that we build in any permutation, right?
Correct.
Okay, and then what is the 1 out in front?
This 1 accounts for, there's only 1 choice here. Because the way I want to express is, I want to express the number of choices per cell, and then have a product of those possibilities to come up with the actual number of outcomes. Yep.
Is this how many possibilities we're subtracting from the total valid
Yes.
possibilities?
Yes. This is the number of sequences that only meet one of the constraints, but not both. Okay. So we have to take out this many out of the number that we have already come up with. Okay? So when we go back to the equation, which is which looks like this, okay? So we have to now say the total number of cases that will meet our requirements is going to be n minus r minus 1 times n minus r minus 1, the factorial of that. But we have to subtract the ones that do not meet both requirements. This number, can everybody see it, including people in the back? Can you see this portion or not? Yes? No?
Yes.
It's good?
Yes.
Okay. Okay, so this number accounts for the number of sequences that meet at least one constraint. Okay? Because that's the same problem that we had earlier. But we have to take away the number of sequences that meet exactly one constraint because it will fail the other constraint. This number is the number of sequences that will fail the second constraint out of these ones. So we have to subtract that one, which is minus n minus r minus 2, n minus r minus 2 factorial. Is that okay? So this is just the number of ways to start with a 2 when we have n equals 10 and r equals to 6. Yep?
But the given number, is that n minus r factorial?
Say again.
Is that n minus r factorial, or is that n minus r minus 1 factorial? There's before the minus, the left.
Before the subtraction,
Yeah. That's n minus r factorial.
it's n minus r minus 1 factorial. It's the same number that we saw earlier.
No, what I mean is both combined gives you n minus r factorial.
If you combine both,
So you're off by 1.
So n minus r minus
okay, are we still good? Okay. But this is only the number of core sequences starting with a 2 when n equals 10 and r equals to 6. How many other subsequences do we have? Okay, well, we don't have to enumerate all of them. We can, one can start with a 3, and with an 8, can start with a 4, and with a 9, can start with a 5, and with a 10, but that one we don't want to count. So there are only three ways to start three ways to arrange the sequence of 6 numbers that will require 2 constraints, because the other 2 cases only have 1 constraint. Is that okay? So now what we need to do is to look at this number, this entire number, put parentheses over the entire thing, and say that we have n minus 1 way to do this. But then each one has n rotations, and then times 2 for the mirror images. So the times 2n is universal, so I'm not going to put it here. Is that okay? Yep.
So like for the sake of like simplicity, because I know it's like not mathematically simplified, but we have n minus r plus 1 total ways of listing total unique sequences of r in the beginning.
Yes.
Man, words are hard. So
That's hard to say, yeah.
Yeah, total unique sequences of r length in the beginning.
Yes.
So could we rewrite n minus r as minus 1 as n minus r plus 1 minus 2?
Yep.
Chop off the end.
Oh, okay. So you can simplify how it looks. Yep.
Yeah, so it makes it like, it's not mathematically simplified, but it's kind of methodology.
It makes the equation simpler. Yep. It's more elegant. Okay. That's good too. But this is the rationale, how the number comes out. Okay? So this is one part of it, and then the other thing that we derived earlier is the other part. So I know this is going to look kind of nasty, because when you look at this number, This is the total number of ways. This is the total number of chord sequences, or the chord ways of assigning the sequences for n equals, for any n and any r, but r has to be less than or equal to 2. Excuse me, take it back. N minus r has to be less than or equal to, greater than or equal to 2, because otherwise it doesn't make any sense. Okay. Question?
I got like a completely different answer, but it works.
Okay.
How would you grade it?
Well, first of all, I would like to see that you guys have validated your own answer. So you can, if you have already written a generate and test program, you can give me a table and say, okay, empirically we know these numbers, these are the answers, okay? And you can then you can reason out how you derived your formula, and then you can say that this formula works for all the cases that I already know. Yes.
Like I just got 2 over k factorial as the answer, and like how I got that is it's 2 times combination over permutation, because we know with every combination of our numbers, there's going to be 2 sets of those that are increasing or decreasing, and then you divide it by the total of ways to arrange those numbers, which would be permutation.
Well, when I grade it, I'm going to plug it in and see if it works with the numbers that we already know. Okay. But that kind of hinges on your generate and test program was implemented correctly first, so you actually count the numbers correctly. Okay, I know some of you have a table, so we can actually cross-check these numbers. Yep, go ahead.
One more time, the part before the plus.
Before the plus.
Because we put two parts together.
Yep. Mm-hmm.
If you could go over what those 2 parts were one more time.
Okay, sure. So let's just separate these 2, and we'll say this is part A, and this is part B. Okay. So part A is what we did a little bit earlier, where when you only have one constraint and not both constraints. Okay. So when you look at a sequence, okay, I'm just going to look at a sequence in a much more general way, so we're not going to actually assign numbers. So this part is the actual sequence, okay? So let's say this is the sequence of R items. So there are exactly R items in sequence right here. But the first part of the equation, which is this part here, this n minus r minus 1 is telling you how many numbers can take on this spot, which is right after the sequence of r numbers. Okay, we know this is n minus r. Well, normally it is n minus r, because out of n numbers, r is used. So normally we have n minus r choices for this slot here. But of these numbers, 1 will continue the sequence, which is not what we want to do. So that's why you have to subtract another 1 and say that, okay, we can have any number other than the number that will continue this sequence. Is that okay?
Yes.
So this accounts for the number of choices for this very specific position. Well, what about the rest? Okay, first of all, how many numbers do we have left? We have n minus r, because we have n minus r minus 1 that is remaining here. But the ordering of these, I don't really care, because I can end with anything here, because nothing can precede a 1, so I'm not worried about this end. That's why I said that there's only one constraint in this case. So that's why there are n minus 1 factorial permutations for the rest. And that's how I come up with the number of n minus r minus 1, the whole thing, times n minus r minus 1, the whole thing factorial. The 2 times has to do with, there are 2 patterns that fit this particular description. If you start with a 1, it fits that description because the n now has no constraint. On the other hand, if the first part here ends with n, then you also only have 1 constraint because nothing can follow n. And that's why there's a 2 times. Yep.
that, the big long equation we came up with, that tells us exactly how many things have a sequence of R, right?
Up to, yes. Up to. You can have subsequences of even, you can have
Right.
fragments.
But it doesn't tell us how much has at least a sequence of R. It tells us exactly how many have a sequence of R.
It will tell us the number of outcomes where the longest sequence is R.
Right, okay.
Yep. The longest sequence is R in this case. Yep.
Can you go back to
The big equation?
the bottom one, yeah.
Yep. So we just explained part A. Yep, go ahead. Oh, okay, you just want me to scroll there?
Yeah.
Okay, I thought you had a question about that part. Okay.
Sorry.
Okay, part B. Okay, let me just take a look at part B here. So part B is explaining, okay, what if we have two constraints, okay, instead of one constraint? So the first item or the first number out of the highlighted portion, which is n minus r minus 1, is simply asking, we have two patterns that fits this particular way of only having one constraint. But how many ways can we arrange a sequence of R so we end up with two constraints? Well, the first number can start with a 2, can start with a 3, and so on. And I think the last number it can start with is n minus r. Let's see, n minus r plus 1. Okay.
Yeah, plus 1.
Yeah. No, if you have a plus 1, that falls into the first case again. So I think it's just n minus r.
Yeah.
Okay, let's figure it out. Okay, when n is 10 and r is 7, then we end up with 3 being here. Is that the case? Nope. We have a 4, so we have to have a plus. No, the 4 does not be the case. So n minus r is correct. Okay. So the question now is, so if you count, how many do we have? 2, 3, 4, all the way up to n minus r. And the answer to that question is there are n minus r minus 1. If you just count the number of rows here, there will be n minus r minus 1 rows. Is that okay? Because it's n minus r minus this number, but you have to add 1 because we are not looking at the difference. You know, we are counting the number of items. So this number is where I come up with this n minus r minus 1. If you focus on 1, then it looks like this. Okay, it looks like this. We still have a sequence of r, but we have two constraints. There's a certain number that cannot end this part. There's a certain number that cannot continue the sequence of r either. Is that okay? Yep.
Can we have more than two constraints?
We only have two constraints because we just want to make sure that the longest sequence is only of length r. So we don't want anything to continue this particular sequence, which places one constraint here and one constraint over here.
But if you have like a small r and a really large number, then there's going to be multiple of constraints inside.
Correct. That's why you only have to work up to the case. You only start with the case where r is greater than n divided by 2. Because when r is less than or equal to n divided by 2, then you end up with those problems. And I don't want you guys to deal with that.
Yeah, that was the biggest headache for me.
Okay. Who first? Okay, go for it.
Did we account for the other way around? We multiply by 2, right? We need to multiply by 2 because we have to go over the other way.
The other way.
So the number
just saying the bigger.
goes 1, 2, 3, 4, 5. So now it's the opposite.
Ascending and descending.
Yeah, exactly. Yeah.
That's the times 2.
Yeah.
We'll take care of that later. These are basically what I call these core sequences, which means when you have a set of core sequences, none of the sequence can be the result of the combination of rotation and mirroring of the other sequences. So these cannot be replicates of each other. There's no way they can be replicates of each other. Yep.
We haven't gotten to the final solution yet, right?
No, not yet. But I'm just going back to explain, the equations. Yep, go ahead.
I'm confused on, sorry, Professor, why is it n minus r minus 1, like the bottom?
You mean this one?
Yeah.
Because I'm just counting. We can have a sequence of R that starts with a 2, start with a 3, start with a 4, start with a 5, all the way starting with n minus r. So now the question is, how many sequences are we talking about? And this is the number of sequences.
So like going back to the example, let's say r is equal to 7.
Uh-huh.
So that means that it
2,
would be
right? It means there are 2, because when the sequence starts with a 2 and when the sequence starts with a 3, these are the ones that meet that requirement of having 2 constraints instead of 1.
all right.
Okay? Because the sequences that end up with 1 constraint, they are taken care of already.
Right.
So we're only taking care of the ones in between that actually has 2 constraints instead of 1. And the way I take care of the 2 constraints instead of 1 is to subtract the portion that will meet 1 constraint but not the other constraint. Yep. So are there any questions? Yeah, go ahead.
So with that, the highlighted equation, would that work for even cases like when n is equal to like 12 or any number? Would that equation still work for like any number?
It won't work for small n's, but it will work for n's that are 3, 4, or more, I think. Okay, so we'll go ahead, instead of writing this whole thing over and over again, we'll just say that grn is this thing, because we'll need that. So in your question, your question is to figure out the chances, right? Your question is figure out the chances of having at least a sequence of R or more. That's the question. So how do you work this into it? Because the G is only telling you the number of outcomes that has a longest run of, or the longest sequences of R elements. Okay, that's what is figured out. Yep.
You could use that, so it's sort of like you plug in first R and then R plus 1, all the way up to n minus 1,
Yep.
or the value R.
Yep, so you basically use a summation. So you say, summation I starting with R, sum up to n minus 1, and then you plug in the G equation here. So you have G, I, N, and then you take this entire summation, which will give you the total number of outcomes with a sequence of at least R elements, and then you divide it by the cardinality of omega. Omega is the set of all possible outcomes. In other words, in this case, we have n slots and n numbers. How many ways can you put n numbers into n slots? N factorial, exactly. So n factorial is here. So if someone asks me for a answer, that would be the answer, but it only works for cases where n is a certain number, because when n is small, it doesn't work. Yep.
So were we supposed to divide by n factorial? Because I wrote the function, but I didn't divide by n factorial.
Well, technically speaking, you have to divide it by n factorial, because I'm asking for the chances of ending up with a assignment where you have at least R numbers in the sequence. So technically speaking, you have to have the divided by n factorial. But the minor detail is not going to be that important for this one. I'm not going to look at this and go like, oh, okay, you have a divided You don't have to divide by n factorial, no points. Move on to the next one. That will make it very easy to grade because I think pretty much the whole class is going to get a 0. Because everyone's going to make some mistake somewhere in a proof like this. Yeah.
What if we understood it was a g of r of n function, but then completely whiffed what g of r of n was in actuality? Because I feel like
99% of people.
Yeah, I feel like I just.
Well, the important part is to figure out how to count, okay, which is working out these things. So I would say that's still going to be kind of like an important part of the answer. The summation part, is kind of important, but that's only after you figure out what the G is. Yeah. Okay. Yep. Go ahead.
So you said the summation part is really important, but I came up with 3 different forms. The one, obviously when n equals r, you just do 2n.
Yep.
And then another form for when n equals, or r equals 1/2 of n. And then the other form was for between n equals r and n is greater than r divided by 2. Or r is greater than n divided by 2. Sorry.
So you did not use summation?
I didn't use summation. It was really short, but it got the right answer. And I only went up to 10. I got up everything up to 10, and I didn't. My table, I didn't go past 10 when I was doing the table.
So that's even better.
But because you kept saying you need to do sums, and when I came up with it, I just did really short.
Okay.
But you don't need sums.
Well, if you don't need summation in your answer, that means there's a way to simplify this one to your answer. So I guess we can make that the next homework assignment. Simplify this, so it becomes that. But I'll take a look at your answer because that sounds interesting to me. Because when I see your answer, I probably can figure out why the 2 are actually the same number. Because I tested this one too, and it works out, and the rationale works out too. So you might have a different way of arriving to the same conclusion, but the 2 numbers should be the same. If they're the same, there has to be a way to derive one from the other one. Yep, go ahead. Oh, you had a question? Oh, you did not. Okay. Yep, go ahead.
Is this homework gonna be worth the same as like the other homework, or is it gonna be worth more?
I think it's about the same. All right. So are we ready to give this one a rest?
Yes.
Please.
Yes.
Well, I think this particular question is also a, I would call it a soul, searching kind of question. Where you don't have to go to Tibet, you just have to stay home and work on the question. I think, how you respond to this question. Now, you don't have to tell me how you responded to this question, if you enjoyed working on this one, almost to the point of, I'm going to drop my other homework assignments, but I want to get this one done, you have the inquisitive nature that will make you a good choice as a computer scientist, okay, the research kind of people, okay? If you look at this question and say, oh, this is so trivial, I'm done in 5 minutes, you are definitely a research scientist material. Okay, so I just think that that's probably a little bit revealing, okay, because if people look at this question and just looking at the question is giving them headache, not even working on it, just reading the question itself, then research scientists may not be the best career choice. So, and there are choices. We all have to make choices in life. We just have to kind of make the choices that fit us. Like if I were to decide and go like I'd like to get rich, and I want to be famous, I want to be an NBA player, that probably will not work out very well for me, unless they start a sub 5'5" league just for people of my height, okay? Then even so I would not have a chance because I can't really shoot or run.
Disabled league. Disabled league. League for disabled.
We'll just call it height constraint. But I think I think the basketball league really should do that. Is to have different leagues based on physique. because people with different physique may not compete the same way. You can some may be more entertaining.
Like weight classes for wrestling.
Exactly.
But they actually do though. People like shorter height actually compete with people with height all day. So
Not the same way though.
not the same way, but they fight in a different
Watching
way.
Curry is not the same as watching Shaq.
It's interesting to see tennis matches. Do you guys remember what's the name of that Chinese guy? Peter Chang.
Yeah.
You guys know who I'm talking about? The guy who would not give up. He's really weak as a man player, so his serve is really slow, but the guy will run where most people would give up. So he would just run and run and run and run. People would go like, "Oh, that's way too far. I'm just going to let this point off." He would just run. He would run and catch it, and he would run the other way. So he just wears down the opponent. That's his strategy. Is I'm going to wear down my opponent, both physically and mentally. Because most players go like, wham, I have a super serve, or I know you cannot get this one, and he would just catch it. Like, whoa, that is way too fast. Let me swing it to the other end of the court. And he will run all the way to the other side. So psychologically, to the opponent, it's just amusing. It's like, wow, he can really run that fast. Let me try again, all the way over there. And he'll run, and then serve it back. Now I have to look up his name.
Peter Chang.
Peter Chang?
It's not.
It's not?
No.
Tennis player, Chinese. Oh, those are the new ones. Huh? Is it Peter? It has to be the wrong one.
You're the female.
The female.
Well, unless, okay, Chinese.
Like you never knew you was
But his nationality is not Chinese. Maybe that's why.
Michael Chang?
Michael Chang, that's it. Thank you. Michael Chang, C-H-A-N-G. There we go. And let's see if we can find some of his signature matches.
Highlights. Put down highlights.
Oh,
Michael Chang highlights.
where?
Oh, that's a great.
Go back to YouTube.
In YouTube, just put down highlight.
Oh,
It's highlights.
oh, this one is highlighted.
That's promising. Why have you already muted?
Best of.
Best of, there we go.
So which side is he on?
I think you'll find out if he's the one who runs the most. I would say he's the far end one. Do you see how his see how his opponent is just running a little bit, maybe half his distance, and he's going all over the court. Yeah, he just wore down his opponent. It's like, is that a gas?
Yeah.
Oh, yeah, that's easy to wear down. He's just an easy one to wear down. Just psychologically, if I don't get the match over in 2 swings, I'm done. I'm going home.
Check out Scott Sterling.
Oh yeah.
Soccer one.
So I think he's serving this time. You can see how weak his serve is compared to the opponent. But look at his run. Yep. So I think that's it. That's interesting. Well, the one who's going to run. Who's the one who's going to run the most? Keep running. Yep. Yep. So when you lack the strength, to return the serve, You just have to run a lot faster.
Imagine that we're rebroadcasting a best of to YouTube from YouTube.
We'll make it a recursive algorithm, which brings us to the next topic. All right. Okay, so I went through all these explanations. I will grade your answers because apparently there are more elegant ways of looking at this and come to the same conclusion. Sorry?
And less elegant.
Yep. Okay, well, we'll take a look at those things, but I just want to explain how I, solve this problem or how I look at it. How many people have done this? If you haven't done it before, I would look for it and see if you can do it. So it's called the IBM Programmer Aptitude Test. Aptitude Test. And it is I think it's in image form. There we go. So this is one of the links. This is for years. Okay, for years IBM gave people these tests to see whether they are well suited to become programmers or not, coders or programmers, however you want to call that. And when you read these questions, there are very few, if any, words. Okay. Most of these are like giving you a sequence, and then you have to continue the sequence. So you have to figure out the pattern, and then figure out, okay, the next one, okay, I can see the pattern. The next one has to be this number, or has to be this shape, has to be this, color and stuff like that. So word is not even an issue. Language is not an issue with these tests. So if you're bored, you might want to give these things a try. They're kind of like small, tiny little puzzles. It has to do with sequencing, just numbers, and the way you recognize a pattern in something. And apparently, the tests are very accurate. People who ace these tests usually turn out to be top-notch programmers, coders, software engineers, and that sort. Okay, so you might want to take a test like this, just to see how you do in these tests. Okay, it's an aptitude test, which means it probably does not require a lot of training or studying. You just kind of go in with a make sure you have enough rest. That's the only thing that I can possibly think of that would affect the result of the test. But there's no studying. There's nothing to study. It has nothing to do with programming languages or concepts or things they can read in the book. So you might want to give it a try. I think this will be kind of interesting. Okay. Continuing on to recursion. Okay. Now recursion is an interesting thing, and I will go to, well, let's start with recursion first, okay, just like this one here. I'm not going to read this part, okay? Well, I guess I will, because the first one is just in n factorial, and we're expressing n factorial recursively. Because when you look at the definition here, n factorial can be expressed as n times the factorial of n minus 1. In other words, we are looking at a bigger problem, which is n factorial, and we break it up into a smaller problem, which is n minus 1 the whole thing factorial, plus some additional operation. Okay? And that basically defines what a recurrence relation is, which leads to recursive algorithms. How many people know of recursive algorithms from your other classes? So quite a few, okay? And what is the most interesting one that you have seen?
Factorial.
Fibonacci number, factorial, anything else?
You can use them to find binary conversions.
Binary search can also be done recursively. Binary search tree can also be done recursively. Okay, so trees are particularly interesting because what a tree is. Okay, so let's just create a binary search tree. Okay, this is not data structure, but I want to use it as an example to illustrate what recursion is. Okay, a binary search tree is created by placing numbers following one specific rule. Whatever is going to the left-hand side is less. Whatever is going to the right-hand side is more. Okay, you can flip the ordering. Okay, just be consistent within the tree. So let me just give you a random sequence of numbers. Let's say we have 2, 10, -5, 4, 6, and then we have a -1 and 16. Okay, that should be good enough. Okay, so the tree originally is empty, which means the 2 becomes the root of the entire tree because there's nothing there to begin with. Then we see a 10. Which side should I go? The right hand side. Go ahead.
Is there a darker marker?
Oh, okay. Let me. Okay, is that better?
Better.
Probably not.
A little bit better.
Well, we don't have to deal with this much longer because according to Amazon, I should be getting my document camera today.
Oh.
So on Thursday, I will have my very personal document camera so that I can use a piece of paper. Whatever I draw on the piece of paper is what you will see on the projector, and it will also be recorded. Once again, I have confirmed that teaching is the only occupation where you steal from home to go to work. Okay, so the 2 goes here, which is in the center, but the 10 is going to be here because 10 is greater than 2. Okay, greater than goes to the right-hand side, less than goes to the left-hand side. The next number in the sequence is -5. -5 is less than 2. There's nothing on the other side of 2 just yet, so -5 becomes the left-hand node of 2. Yep.
How did you determine again from which number to start?
I'm just reading these numbers in the
first
sequence.
one.
Yeah, 2, 10, -5, the next one is 4.
So it's just in a row.
Just to.
It's just random.
Okay.
Yeah. So the next one is 4, but when you look at 4, you have to see where 4 is going to fit within the existing tree. 4 is greater than 2, but it is less than 10. So 4 is going to be here. Is that okay? Next one up is 6. 6 is greater than 2. 6 is less than 10. I cannot be here because 4 is already here, but 6 is greater than 4. So 6 is going to be here. -1 is less than 2. -1 is greater than -5. So -1 is going to be here. And then 16 is greater than everything else. But then you have to say, okay, it's greater than 2, it's greater than 10, so 16 is going to be here. So typically, if I ask a question like this, it's pretty easy to answer. But if I ask a question in a slightly different way, like if I want the next value to go here, what value can go here? Now, obviously, there are many, many numbers that can go here, but what can go here?
3.
3 can go here. What about 1?
No.
No, because 1 is going to be on this side. Okay, so 3 is greater than 2, 3 is less than 10, 3 is less than 4. So yes, definitely 3 can be here. Okay, so this is the nature of a binary tree. Okay, it's not a I think I said binary search tree. It's a binary tree. It's a binary search tree. Yep.
Can you have like 2 of the same number?
Say again.
Can you have like 2 of the same number?
No, you
So I
can't.
have another 2.
No, you can't. Yeah, it'll be redundant.
It'll be redundant, but I'm just thinking, does it work? Because instead of using less than and greater than, I can use less than or equal to on one side.
Yeah, you can have equal. You can send it either or.
Yeah.
You can send it either to the right or to the left according to your choice.
It will still work, right? The traversal will still come out sorted.
They can't both be less than or equal to though, right?
Huh?
No. You just have to decide which way you're gonna go, the equals.
Yeah, what happens when you balance the tree is it's gonna crash because you're gonna have two of the same number.
No, you just have to put it on one side.
No, just the condition. What you're trying to store. Like,
But it will
Yeah.
still
Yeah,
sort it
yeah,
and you can still find it correctly.
Yeah. Because each one of those nodes could be the beginning.
But what does this have to do with recursion? Okay, the first thing is the representation itself has recurrence in it already. So we are not even talking about algorithm. We are just looking at the shape of this thing. Because when you look at this entire thing, root-in at 2, it is a tree, okay? When you look at the one starting at a 10, it is a tree. When you look at the one starting at a 4, it is a tree as well. So that means the pattern or the structure itself is a recurring pattern. Okay? So that's important because if the representation itself is like this, it means it is likely or at least possible that we can find a solution that is recursive. Is that making any sense?
Yes.
Okay. So let's take a look at a recursive algorithm in this case. Okay, I just want to see if a particular value is in a tree or not. Okay, and I just need to look at the pseudocode. How do I do that? So we are not looking at something that is going to compile. We just need to look at something that will, well, just represent the correct approach. Okay. So this is going to return a Boolean. Okay, find a particular value in a tree. Okay. So how do we write this subroutine? Well, we start with terminating cases, where we say, okay, stop, there's no need to search anymore because of these obvious reasons. Okay? So we can say if T is empty. In other words, if there's nothing in this tree, well, there's no way I can find a value in an empty tree. Okay, so local variable result. So say the result is false, because an empty tree cannot have a value. Yep, question? Oh, I thought you had a question. No, okay. So if the tree is not empty, that means I'm looking at a node, because the root of a tree is a node, it has a value. So the first thing I'm going to look is, hey, maybe I get lucky. Maybe this is the number that I'm looking for. Okay. So I'm going to say if value of t, or the value of root of t equals to v, then we are all set. The result is going to be true. Okay. Okay. What about the else case here? Okay. The else is basically saying t is a tree that is not empty. It has a root. The value of the root is not the value that I'm searching for. Well, but every tree has two sides to go. Like 2 here has one side rooting at a -5, the other side is rooting at a 10. So I have to direct it to one way or the other. Okay? So that means I have to compare. So now I have to say if the value of root of t is less than v. Mind you, this is not the most efficient way to write this code. It just illustrates the rationale behind it. So if it is less than the value, or the value is greater than, that means it's on the right-hand side. So what I'll do is I'm going to use the same logic, use the same subroutine or function, find, to find exactly the same value, but this time I'm going to use the right subtree of t instead of t. In other words, I just broke the problem into a smaller problem and pass it along to the same algorithm. But this time, you just have to solve a smaller problem. So if I can continuously or step by step consistently reduce the problem into a smaller problem and a smaller problem and a smaller problem, eventually it will get to one of the cases where I can answer directly. Does that make any sense? So just to finish this, before we leave today, the else is going to be about the same as the then, because we have already taken out the case where it is equal. So this time we just have to look into the left subtree of t. Is that okay?
Yes.
This is a recursive algorithm. And the interesting thing is every algorithm can be turned into a recursive algorithm, and everything that is recursive can turn into an iterative equivalence of the recursive algorithm. So internally, they can express the same type of solutions. It's just that sometimes it's easy to express recursively. Now remember, this is also the long way to do it. If I have ternary operator, this whole thing can become just one single return. Maybe we can make that a homework assignment. Alrighty. I'll see you guys on Thursday, and we will have the document camera on Thursday.
Yes.